Right. So just again, a good morning to all of you. Listen, so the way that our situation has changed at this stage is that obviously this week is still going to be online, and we have our Zoom classes and work as has been for the past 3 months, and so will next week. And then you'll go on a break, and if everything stays the same like it is now, we will return to school on the 13th of June. So we're holding thumbs. That is depending our president's announcements. So I would like us to also write a test. And the test will be on chapter 13 and 14. Right? Chapter 13 and 14, so the introduction of the different kinds of functional groups, drawing molecules, naming molecules, similar to what we're doing over here, and then our fuels and alkanes, the reactions on alkanes.
So I'm not ready for that yet.
Hey?
I'm not ready for that yet.
I know you're 65% there, Liam.
No, not even. I'm not even close. I promise you, I'm like 50. If
Right.
lucky.
Just to let you know, this that you're doing now, this is not in the test, okay? So it's the previous work. And on that, I'm still going to give you a worksheet, Liam. And that worksheet will work through on Tuesday when I see you again for chemistry. So the test must be after Tuesday. So let it sink in a bit in your mind, and at the end of this class we can quickly look at a day in next week that we can do the test. Okay, let's, after that initial shock, let's look at our questions, end of chapter questions of chapter 15. Now we start off simply by naming molecules. And can we name this first one? And hopefully the answer would be yes. Yes. So we number 1, 2, 3, 4, 5 carbons. That is a straight chain, my longest chain, and well, the parent is it's pent. Remember, my double bond must have the lowest number. It's between carbon 1 and 2, so it's pent 1 ene, and that's my name. Right? There's nothing weird happening to it. Simple, straightforward, pent 1 ene. Must include the number because the double bond could be between any other 2 carbons as well. Right.
And sir,
yes.
When they tell you draw the structure of pentene, what would you draw then? Like if it's not like there's no number.
I will still keep it then at carbon number 1, unless they give you some other information. They will usually give you other information. Okay, in an exam. Sometimes the book is stupid and it doesn't, but we'll deal with it. Okay, let's look at any other questions. Good. All right, let's look at this next structure. So skeletal formula. Remember, each tip of a little stick, let's call it a stick, represents a carbon. So that means there's a carbon, 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 there's a carbon. So how many carbons? 1, 2, 3, 4, 5, 6. And we have hex. We need to number it again so that my double bond has the lowest combination of numbers. So this is 1, 2, 3, 4, 5, 6. So on carbon number 2, so it's hex 2e. Happy with that? Let's look at III.
It's this thing that got me, sir.
This thing. All right, let's just
look at that thing. That's a mountain.
Well, it's actually 2 mountains, but you know, carbon, 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 carbon. Just to help you in the beginning to see it. So how many carbons? 1, 2, 3, 4, 5, 6. Okay, so it's again hex. I will always start with my parent chain. Then, from which side? Carbon 1, 2, 3. Okay, so then the double bond is on carbon number 3. Let's check from the other side. This was easy. We could have seen which side. 1, 2, 3. Oh, it doesn't matter. Hex 3 E. Right? Hex 3 E.
So why is
Yes.
it straight? Why is it not a? Why is it like peaks?
Do you know what? It's just the way that the computer sometimes draws it, because it takes in the bond angles around it. So, you know, and that's the only reason I can give you. Because when I produce on my program that I have, uh, the computer takes it in because it's been programmed to take in the angles around each one of it. So, and that's how it produces it. So that's how it looks.
Okay.
So you could draw it, boom, 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 boom. You could draw it if you drew it like that, for instance, 1, 2, 3, and then 1, 2, 3. It could look like that, for instance, as well. If you drew it, if I would draw it, that's most probably how I would do it. Okay, and then, wow, what a stupid question. I'm very sorry. We're busy with alkenes. The chapter's name is alkenes, and then they throw out something like this. What is this? This is a triple bond. We don't do triple bonds. Triple bonds is not in our syllabus, but by heck, let's do it in any case. How many carbons? 1, 2, 3, 4. 4 is beautiful. A triple bond ends with "-ine". So 1, 2, 1, 2, so 2-ine. Right, so, but forget about this. What a silly book. It's not part of our syllabus. However, the next one is, what do they give us in here? It's a cyclo, and it's got a double bond. Where do we start numbering? Well, same rules apply. We need to give the lowest combination to my double bond. So what's the lowest combination? Well, 1 and 2. 3, 4, 5, 6. Doesn't matter which side you go around. Well, yes, it does, but only if there's other side chains or constituents on this cyclo. But for this, no, it doesn't matter. You could have gone anywhere around. The double bond is between carbon number 1 and 2. There's 6 carbons in there. So this is cyclo hex 1 E. Again, hex, number of carbons. Cyclo because it's in a circle, and 1-ene because my double bond is between carbon number 1 and carbon number 2. Happy with that? Right. Let's move on to our question number 2. Oh, sorry, there was a B part as well. I forgot about the B part. Let's quickly do the B part. I was so enthusiastic about getting to my reactions. Let's do the B part. Let's say write structural formula for these compounds. And the first one is propene. Propene, and again, now propene 1, 2, 3. I'm drawing the displayed formula to make it easier. Well, listen, there needs to be a double bond in there. So 1, 2, 3, 4, 1, 2, 3, 4. And that's how it's gonna look like. There's no dip dip. Okay, so how would this is the displayed formula? They want the structural formula. So CH2 double bond CH3. That is the way that we'll give structural formula. So it's easier to do the displayed formula and quickly get the correct structural formula from that. Let's do I.
So, oh no, okay.
Is that okay?
No, it's fine, it's fine. All good.
Oh, right. Do interrupt me because sometimes I'm on a roll. And then, as I said, this is my favorite part of chemistry, and I can keep you busy up until next year with this part because it's nice to linger on it. Cis pent 2-ene. Okay, so how are we going to draw cis pent 2-ene? Let's do the structural part first of all. So carbon number 2 and carbon number 3's got my double bond in. So this means there is a carbon on top there, and my other 3 and 4 is also on the same side. There's hydrogen, there's a hydrogen. So that's how my cis would look like if I drew the displayed formula. So what about, yes?
I have a question with the cis and trans. Do they have to be exactly identical, the two side groups, or not?
No, they don't have to. Like for instance, over here, we have a methyl and an ethyl. It's just they are to the one side, while the hydrogens on this side is to the same side. So no, they don't have to be identical.
Okay, thank you.
So why is it carbon 2 and carbon 3 in the middle?
Because it's pent 2-ene. And you always get the lowest number of the two carbons where your double bond is. You wouldn't in any case have a cis or cis-trans isomerism with a pent 1-ene. You can't have that. And you have two of the same groups, a hydrogen and a hydrogen on a carbon. Right? So when we name a molecule, we always give the number in there, the lowest carbon number that my double bond is attached to. So if it's a 2, then it's between carbon 2 and 3. If it's a 1, then it's between 1 and 2. Makes sense to you?
Yes, sir.
Okay, perfect. All right, let's give the structural formula because this is what it asked, right? So CH, double bond, CH, and I'm just going to give the CH, CH3 to show that it is still in my cis transformation. So structural formula means not all the bonds are shown. So I don't show all the bonds connecting like that. So all the bonds shown, displayed, not all the bonds shown, structural formula. Let's look at III. It says cycloocta 1357 tetra E. My goodness, they ran out of ideas. That's the only way to get to something like that. Let's draw. 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. I ran out of space, ran out of ideas. Something like that. So an octahedron. I can't draw an octahedron. So let's number carbons. 1, 2, 3, 4, 5, 6, 7, 8. Where's my double bonds? Between carbon. So if they state 1, it's between 1 and 2. If they say 3, it's between 3 and 4. If they say 5, it's between 5 and 6. And when they say 7, it is between 7 and 8. So there's my double bonds. Now we need to make sure that we have the correct number of hydrogens in there because it's 3 bonds to each carbon. So what does that mean? It means each hydrogen will actually still have what? 1 hydrogen. I'm going to do that because I'm going to cheat and say, well, here we go. That is my structural formula for this compound. So CH, 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 CH with alternating double bonds in there. They really ran out of ideas. Guys, you're not going to get something like this in the exam. Forget about it. So that is, in essence, the structural formula.
So what does tetra mean?
tet means 4 double bonds. 1, 2, 3, 4. There are 4 numbers, so tet means 4 carbon.
Okay, cool.
Perfect. 1 IV. 2-methyl pent-2-ene. Okay, this is something you will get in an exam. Let's start with pent. 1, 2, 3, 4, 5. There's 5 carbons. Let's just get back on screen. Right, 1, 2, 3, 4, 5. Let's number it. It makes it easier. 1 it is there. So 1, 2, 3, 4, 5. There's 5 carbons in there. A 2-methyl and a 2-ene. So 2-ene means there's my double bond, and a 2-methyl means on carbon number 2 there's a methyl group. Okay, so that was simple enough. Let's add in my hydrogens just to get the full displayed formula. Remember, always 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Done. 1, 2, 3, 4. 1, 2, 3, 4. And there's my complete structural, complete displayed formula. What about my structural formula? Well, now we can say CH3. Then there's C, and in brackets you put CH3. That's a side chain connected to it. Double bond, CH, CH2, and a CH. And that is how your structural formula for this compound will look like. It's easier to start with displayed and go to structural formula. Right? A question in an exam may ask, like this question, to give the structural formula. If you then give the displayed formula, you will lose a mark. Again, just 1 mark because it's interpretation if it's a 2 or 3 mark question, but it's not a mark worth losing. You guys can do this. Happy with this? Let's move on to question number 2. Sorry, I lost totally out on that B part. Right. Then they give us, and guys, this is nice chemistry.
No, it's not.
Liam, stop bursting my bubble, man. I mean, seriously.
You.
What do they ask us? They say, write down the reagents and conditions represented by reaction B, D, and F. B, D, F. Guys, and this is the only way that you study organic chemistry. Right? You've read through the chapters now, you've made your little summaries, but this is the only way you study organic chemistry is by flow diagrams. You have an alkene, and that you summarize the reactions with reaction conditions. So what is reaction B? Reaction B is hydration. What is the reaction conditions for hydration? Well, we need, first of all, reagents. We need water vapor. We need steam in there. Okay, that's the first thing. We have an acid catalyst. Usually we use phosphoric acid, H3PO4. We have a high temperature. And it's about 300 degrees, 330 degrees Celsius. And we also have a high pressure. And it's about 60 atmospheres. Okay, so those are our conditions for this reaction. This is the acid catalyzed one. There's also one where you can pass it over aluminium oxide on a high temperature and a high pressure. Those conditions would also be great. I checked the book. It's actually not on the book, but it's in my slides. Yes, you may use it. It's a proper way of hydration. What's next? For D, what is D? D is halogenation. It's two different cookies. Halogenation, meaning adding halogens. It's still for electrophilic addition. All of the reactions are electrophilic addition except for the oxidation one, obviously, and our polymerization one. Halogenation, this one is spontaneous, so the only thing that we need is actually chlorine gas. Remember, it's only with alkanes that we need heat clear light. So, enough. And then F is my polymer. Right? Remember, how would a polymer form? A polymer would form around a double bond. So I just left this one out so that we can see it's going to be my CH2 and my CH. That's going to form my monomer. Remember, I asked you to go through this, and then you'll have your CH3 in there. I think the book has it turned upside down from my version of it, but that's your monomer. What's the condition for polymerization? Well, high pressure and high temperature. Yeah?
So can you move your paper a little bit down, please, so I can see that?
Sorry, thank you. Please do.
Oh, okay. Thank you.
Okay. Please ask, please ask. Right, so those are the conditions that they asked. They did the difficult ones with the oxidation in there and the nickel catalyst and hydrogen. They gave that to us. Right, let's answer the next part of the question where they say, write down the formula for the compounds represented by A, by C, and by E. Right, we can do that. What happens when we, remember, electrophilic addition? My hydrogen attacks my double bond, it breaks, and we end up with CH3, CH2, CH3. They just want the product. And listen, they're not specific. They say give the formula, write down the formula. They don't say the structural displayed, so I chose that one. How about for C? Well, again, with C, we've got two products that can form. We've got a major product and a minor product. So major product will be CH3. Remember Markovnikov's rule, CH, and we do the bromine on that one. Again, let's just get it onto screen. So major and minor and CH3. But this would be my major product in there, and my minor product that will also form will be a CH2 with a bromine on CH2CH3. That's my minor. It's two products possible in this reaction. What about reaction E? We have a double bond oxidation, but we have an oxidizing agent, my potassium permanganate, acidified, diluted, it's cold. What's going to happen? We're going to break our double bond and add two hydroxide groups. Let's draw it. So CH2, CH, and CH3, but we add an OH, so it would be a 1, 2, and I think they ask us to name it as well, isn't it? Write down the formula. Name and, all right, so let's do the name. This is 1, 2, sorry, I'm not going to do it that way, old way of doing it. 1, 2, 3 carbons in there, so it's propane. But not N, ending with ol. So propane, 1, 2, diol. There we go. Just get your bearings together. Propane, 1, 2, diol. What are the names of the other two? This is propane. Let's go to our products at the bottom. This is 2-bromo propane. And the other one was a 1-bromopropane. 1. Happy with that? And listen, you've just summarized the chapter. This is a summary of the chapter that you need. So, Liam, here,
Yes, yes.
a summary of the chapter. All of those pages just in this one little.
Hang on, let me quickly take a screenshot, sir.
I've recorded it for you. You can have a look at it later.
Don't worry, I got it.
Okay, let's look at question number 3. Question number 3 seems to be a little bit of a humdinger. We have an alkene that reacts with hot concentrated permanganate, right? Acidified, obviously. The products of the reactions are propanoic acid and pentanoic acid. And now they ask, what is the structure of X? Wow, okay. Let's quickly have a look at this. So this is my scheme, just with X, we want X. Propanoic acid, how does propanoic acid look like? I'm going to do it like this. There's propanoic acid. Oh, let's add the hydrogens for completion's sake. And pentanoic acid, 1, 2, 3, 4, 5. And so again, oxidation takes place where there's a double bond. A double bond is broken. So the only thing that I would look at is, what about a double bond between these two carbons? So that if we look at this molecule, it looks like this. Carbon, 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 double bond. 1, 2, 3, 4, 5. Would it give me these products in the end? Well, let's see. If they break up, what do we get? We get a 1, 2, 3, double bond O and hydrogen. And yes, if I oxidize it further, because there's a hydrogen that I can remove, I get to this product. This means this one is also probable. 1, 2, 3, 4, 5, double bond O and a hydrogen. I can remove a hydrogen and oxidize it further to get to that, because aldehydes can further oxidized. Yes.
Wouldn't we add an oxygen, not remove a hydrogen?
Remember my lesson on Tuesday? Yes, that is correct. So we can view oxidation in 2 ways. We can view it as the addition of oxygen, but at the same time, it's also the removal of a hydrogen. So if there's no hydrogen to remove, we cannot add an oxygen. So that's actually very important to note, that there is a hydrogen to remove so that we add an oxygen.
Okay, yeah.
So yes, you're right. Oxidation is the addition of oxygen, but we need to remove something to add it, and that's the hydrogen. So my 2, or my X in this case, was a 1, 2, 3, 4, 5, 6, 7, 8. So it's octa-3ene. So X, let's just write it in. X is octa-3ene. I wanted to make that one difficult first, then not. I didn't. We got it.
Even I got that one.
Yeah, you see, you guys are actually good chemists. What else is
So that took me like 2 hours.
Hey, what? Wait.
That took me like 2 hours.
Right, let's look at B. It says, draw the structural formula of the product formed when it reacts with cold. What's going to happen if it's cold? Well, we're not going to have complete oxidation like here. We're only going to break one bond and form a diol. So let's draw the product and see where we get to. Play a bit with this. So 3, 4, 5, 6, 7, 8. And it's between carbon 3 and 4. So there is the bond broken. I get an OH attached, OH attached. We can have our hydrogens, well, you know, to complete the picture. Hydrogen, 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 hydrogen. Listen, I think we're going to struggle for time, so I'm going to start a new meeting in a very short bit. So we can finish with this, please. Do they ask us to name this as well? Well, we can name this. It's an octa. Octa and a 3,4 diol. Right, octa 3,4. Let's move on to our next question, question number 4. Question number 4 deals with our polymers. It says we have this 1,1-dichloroethene, and I drew the structure wrong in the book. They actually gave another C in there. So the book was wrong. This is how 1,1-dichloroethene. Eth means 2 carbons. Can't be a 3rd carbon in there, right? Unless they refer to some other bond. And they say it readily undergoes addition polymerization. What is the systematic name for this polymer? Well, remember, this is IGCSE. What you did, if this is the name for the alkene, the systematic name for the polymer is going to be poly. 1,1-dichloroethene.
So do you have to
Yep.
do you have to add the numbers in?
Yeah. It's still going to be that. I think so.
Okay.
I will check for you. As far as I have it, yes. It's just a poly that you add.
Okay.
Okay, so that was A. B, they say write the structure now of a segment. And let's do that. We did it in the previous question number 2 as well. Remember what happens? It's my double bond that break. So if I draw just this part again, it's my carbon, double bond carbon. We have 2 chlorines therein, and I have 2 hydrogens. What's going to happen? Well, we break that bond and we get carbon, carbon, Cl, hydrogen, and it's going to be multiple repeats. And this is the way that they indicated with square brackets. So n times that. So this is called your monomer in there. I mean, then I'll repeat. So guys, we just do addition polymerization. This is, excuse me, in essence it, and just lots of it. So that's where the N comes in. In the little worksheet that I want to give to you, there is 1 or 2 examples of this from our exam questions. Right, C. Would you expect that the polymer to start melting at a higher or lower temperature than polychloroethene? So this is 1,1-dichloro, and comparing it to polychloroethene. Which one will have the higher melting point or boiling points? Melting and boiling points depends on what?
The intermolecular forces.
Intermolecular forces. Is there a difference in the intermolecular force present between these molecules?
Yes, the number A has 2 chlorine carbon bonds.
Okay, so that's true. That's true. But what type of intermolecular force is at play here?
Van der Waals forces, for
Van
sure.
der Waals forces, specifically dipole-dipole, right? So it's the
That's
same
the only.
force. What influences the strength of my dipole-dipole or Van der Waals forces? I hear a little
Is it
I
the
get this, I don't know.
electronegativity?
No, it is the size of the molecule, so molecular size. And because my dichloro has an extra chlorine in, right, there's extra electrons, more electrons, wait, 7 more electrons than actually in a hydrogen. So there's more attachment points with a dichloro. So dichloro would have more van der Waals forces, meaning higher melting and boiling. Okay, guys, I'm going to stop this meeting for now and just start a new one because we have less than 1 minute. See you in 1 minute's time. Okay.